Hi, this lesson is on stretches and compressions of functions. So these are transformers, and you all probably know about these. And transformers just change from vehicles to robots back and forth. So like Optimus Prime is a semi, and he changes into a robot. Bumblebee, depending on which one you're talking about, is a bug, or changes to a Camaro in another one. So anyways, those are transformers, and they change. And that's really all that we're going to talk about is different transformations. What other transformations can we apply to functions? Well, we've already done translations, which are slides. And today we're going to look at a couple of different other ones that we can talk about. And those would be reflections and then stretches or compressions. And so those are other changes that we can make to functions, our parent function, and get new, different kinds of functions and with the same shape and form. Okay, so I want to get into a little bit about quadratics, which you learned about in IM2. You learned how to reflect, stretch, and compress those graphs. And the same rules apply for just about every other function that we're going to talk about. So let's just take a look at some of these and how they work. So at the right, there is the parent function for the quadratic, which is f of x equals x squared. And a couple of things to note. There are some points here at the vertex is there. There's another one, 1, 1, negative 1, 1. Those are some points to keep in mind. So using red, so I'm going to switch to red, we're going to graph g of x equals negative x squared. How does adding this negative affect the graph? So I'm going to use Desmos and just plot that in there. And I've already typed that in there. And you'll notice all it does is flip it around. And you'll notice that there still are a couple of points there, 0, 0 still, and then 1, negative 1, and negative 1, negative 1. So the same points just flipped upside down. Okay, so how does the negative affect the graph? It just reflects it upside down so that I get a point here, a point here, a point here. There would be another one down here just as a guide. But really, I'm just taking this and turning it upside down. It's a reflection across the x-axis. Okay, so then it says in blue, graph h of x equals 3x squared. How does a constant larger than 1 affect the graph? So let's take a look at Desmos again. So if I change this, let's just back that to 3, you'll notice, well, maybe we'll put in the parent function as well. So let's just do x squared. So x squared is in green. The red one, you'll notice here, is a little skinnier. It's been stretched vertically. So now it's a little bit skinnier. It's been pulled up. And one of the points that it lands on is 1, 1 has kind of become, looks like 1, 3. And that makes sense. We've stretched it up by a factor of 3. So I'm going to graph this in blue. I still have this, but now this point has been stretched up away from the x-axis to 3, and this one up here as well to 3. So we're really just moving that up a little bit. I don't want it to be a straight line. Okay, that was not a great graph, but you get the picture. It really just, it's a stretch. It's a vertical stretch. And so that's what that does. All right, in green, if we change that 1 to, I'm going to get rid of these so you can see a little bit better. If we change it to a half, what happens? All right, so let's just add another one here. Let's put 1/2 x squared. Okay, you can see that it widens it. The one in purple there is a little bit wider. And so that's called a vertical compression. And when you press down on it vertically, it gets wider. So when I'm plotting these points, so this was 1, 1. Okay, now that's going to be stretched down to 1/2. So it's going to be a little wider, and that's how we get this function to go kind of like that. And that's how those work. So how does the constant less than 1? It compresses it, and it makes it a little wider. These same rules apply for other functions. Okay, so we've already talked about sliding. Remember, this h value here slides it left and right, and those were kind of opposite of what you might think. And then the k value moves it up and down, and that's just normal. Okay, and now the a value, which we just kind of looked at, if it's negative, then it's a reflection across the x-axis. Okay, and if it's greater than 1, then it stretches it vertically, and what that will mean is it pulls it away from the x-axis. If the number is between 0 and 1, it's a compression, and it should push it closer to the x-axis, kind of like we just did here with this green one. It pushes it closer to the x-axis. Okay, so we're going to use that information and try with some other things. So our directions here say to describe the transformations of the parent functions. Graph with at least 3 accurate points. Okay, so this first one, it says f of x is equal to negative square root of x plus 3 plus 2. Okay, so now the parent function I put in here down here, the parent function is square root of x, and we want a few key points. Now you'll notice on here, some of those key points would be 0, 0, 1, and 4, 2. Okay, so I'm going to plot a few of those, but I need to keep in mind a couple of things. So what's been happening, this negative out in front, what does that do? We just talked about it. It reflects it across the x-axis. So we're going to write that. One of the transformations is a reflection across x-axis. Okay. Another one right here, it's right there, inside, underneath the square root, I guess you would say, is that it says plus 3. Remember, that works in a little bit different way, is that's going to move it then to the left 3 units. Okay. And then outside, or not underneath the radical or the square root symbol, it says plus 2. And if it's out there, it's going to move it up or down. And since it's plus 2, it moves it up. So we just really need to identify these 3 things. And we've done that. And now we can use that information to help us graph. Okay, so the parent function is this one down here in blue. And we want to take that and we want to basically reflect it and then move them to the left. And 3 and then up 2. So I'm just going to start with, I know 0, 0 down here, right? I want to move that one left 3 and up 2. So that's going to end up right there. Now I also know it's been flipped upside down. So this point right here will now end up down here. So I'm going to flip that over. So now I'm not flipping it too far, but I do know it should be, I mean, you might flip it first, but then this would be right there. Okay. And then this other one would be right there. Okay, and now we're going to take and connect those Maybe a little bit better than I did right there, but you get the idea. So there is our exact function right here using those transformations. You can double check it on Desmos if you want, but those are the 3 points that we really want to have in there. Okay. Let's try another one. I'll do this in a different color. Maybe purple. Okay, so again, I put the parent function down here. It's a cubic function. It says f of x equals x to the third. And then this one up here says 2 times the quantity x plus 3 to the third power. So I'm first going to move, I can see down here, I've got a point here, a point here, and a point here. All right, those 3 are kind of my 3 dots. And first thing I want to do is I know that this means left 3. Another thing I have is right here, and this means a vertical stretch. So it's going to pull it away from the x-axis. Okay, so let's maybe do the left 3. I know that I have a point here usually, but I'm going to move it 3 units to the left. So that would now be here. Okay, and then normally, you can see down here, I kind of go up 1 and over 1, and there's a point, and down 1 and over 1, there's another point. Well, if I do that now, that will get me started. So I have 1 here and 1 here. Okay, but it says I have a vertical stretch, and it's by a factor of 2. So that's going to pull it away from the x-axis, which means this point right here is going to go up to 2, and this is going to go down to -2. So that's what I want to change. So I'm going to erase these. And I'll put it here and here. Okay, so I have those 3 points, and now I'm just going to try to do the same squiggle sort of in the middle, knowing that it's a cubic function, but it's not going to be quite as pronounced as it was down with the parent function, because it's been stretched a little. All right, so there we go, and also move to the left. This is what we're trying to do when we're describing the transformations and then using that information to help us graph. Okay, let's try a couple more, and then we'll see if we can write some equations. Okay, this one over here on the left is a quadratic function. The negative, that is a reflection. Across x-axis. Okay, the half would be a vertical compression because it's less than 1. And then this -2 is going to move the graph to the right 2 units. And then the +4 at the end here is going to move it up 4. So I kind of like to start with, well, here's my parent function, right? So I want to start there. Kind of the points that I'm going to look at are these 3. And those are the ones I'm going to move around. I'm going to start by moving around by sliding to the right and up 4. So up here, I know I have normally 1 at 0, 0. So if I move that to the right and up 4, it's going to be right there. Okay, so now that would be my vertex. Okay, now it's been flipped upside down, so I know that it's facing down. And then I also have this vertical compression by a factor of a half, right? 1/2. So when I do that, I really want to be able to think about, well, normally if I opened up, it would be up 1 over 1, up 1 over 1, right? But it's upside down now. So it's going to be this way. Okay. And then instead of going 1 unit down, I'm going to have to go a half a unit down. So it will actually be right here instead, and right here. So now I'm going to get rid of that one and that one. And then we're going to try to draw my quadratic. There we go. Okay, so that is your quadratic function with those 4 transformations. All right, let's try one more of these. Okay, let's see. So absolute value looks like this. It's a V. Important points to note. I like to just kind of do these ones right here. And then we're going to use that as sort of our guide. This one, negative again, so reflection. Across x-axis. The 3 would be a vertical stretch. And then there's nothing inside the x, so we just have the +2. So there is no moving it to left or right, just up 2. Okay, so those are the things I want to represent on my graph. Okay, well, flipping it upside down means I would go like that. Okay, then I have a vertical stretch. Okay, and then up 2. So let's see, vertical stretch by a factor of 3. So this is going to get stretched away from the x-axis. So it's going to end up going down to 3. So here and here. And that will go away. And that would go away. Okay, cool. Except now I also need to do this last one where I go up 2. So I'm going to move all these dots. There, that one goes up 2, up 2, up 2. Now I'm gonna do some erasing. Okay, and then try to draw my line. Okay, and there's that function. We did it. Okay, I hope that is starting to make sense after we've done a few examples. Okay, write an equation for each graph. So the first thing that I like to do is just identify the parent function. So this first one is that function. Which is the square root function. This is the absolute value parent function. And this is a quadratic, so that's what we're starting with for each of these 3. So let's start here. Okay, we'll do green. This one has been flipped upside down. So let's call it g of x equals, I know it's negative. It does not look like it's been stretched at all because notice this point here and that point there aren't changed at all. So we don't have any stretch. So there's no number other than 1 in front. So I can just go square root. And it has been shifted. Normally it starts at 0. It's been shifted to the right. So let's see. Normally that's +1, but remember that's opposite. So this will be -1. So my function there, I guess I should move this over a little bit so it's out of the way. Okay. Is g of x equals negative square root of x minus 1. All right. Let's do this one. Okay, I'll do this. We'll call this h of x. Okay, again, it does look like it's been reflected, right, across the x-axis. It's upside down. Now, normally, I got this point, and then I got 1 and 1, but it's not at 1, it's at 2. So it looks like it's a stretch of 2. Okay, then I need my absolute value. It has been moved to the right 2 and up 4. So right 2 would be minus 2, and then up 4 would be plus 4. And that's it. Okay. All right, the last one. Call this one, this is purple, we'll do this one k of x. Okay, it's facing up, so it's not been reflected. It has been stretched, because it doesn't go up 1 and over 1, it goes up 1 or up 2. So looks like my vertical stretch of 2. Okay, and then it's also been, the vertex has been moved to the left 1 and down 4. So x minus 1 squared, and then minus 4. Don't forget the squared, it's easy to forget that on the quadratic. Okay, there we've just written some equations for some graphs. And just knowing a little bit about transformations kind of puts that all into perspective and makes it a little easier. Okay. Last thing, describe the transformation of f of x. You'll notice here they've done this in the function notation way. So I have the f there. So they're basically saying take this function, the f, that function, and then they've got this stuff in the middle here, and right here, and right here. So we'll describe those transformations. I think I'm just going to work kind of left to right. We know the negative is a reflection across the x-axis. Okay. The 2 is a vertical stretch. So that'll make it a little skinnier. This plus 3, normally move it to the right 3, we'll move it to the left 3 units. And then the negative 1, we'll move it down 1. Slide it down 1. There's all the transformations, and that's it. Okay. Hopefully this makes a little bit more sense. You understand how stretches, compressions, and reflections work. Give this assignment a try. Good luck. See ya.